Hey guys, today I'm going to teach you everything you need to know about the Doppler effect, including simultaneous equations. But before we get ahead of ourselves, I just want to explain a few things. So here I've written the definition of the Doppler effect, and this is straight from your exam guideline. If they ask for the definition, you must write this word for word. It says the change in frequency of the sound detected by a listener because the sound source and listener have different velocities relative to a medium of sound propagation. So basically what this means is if a radio is emitting a sound of 50 hertz, if you run away from the radio is still emitting a sound with a frequency of 50 hertz. The frequency is not changing. But as you run away from the radio, the sound is going to seem softer and softer. As you run towards the radio, the sound is going to appear louder and louder. So the thing that's changing is the observed frequency. The actual frequency is the same. But now, the change in observed frequency, that is known as the Doppler effect. I just want to do a quick recap of your grade 11 and grade 10 work. Your frequency is measured in hertz, and it's the number of waves that move past a fixed point per second. It determines your pitch. A sound with a high frequency has a high pitch. A sound with a low frequency has a low pitch. Low frequency means few vibrations per second. High frequency, many vibrations per second. This is how your high frequency graph will look. This is how your low frequency graph will look. Please take note of how these different graphs look, because sometimes they put in your multiple choice questions, and sometimes they give you a graph and you need to take the values from the graph to use in your calculations. So please understand them. And I just want to make sure you know that this is one full wave. That's one full wave. So the next thing is your period in T. It is the time taken for one complete wave to move past a fixed point. So your wavelength, it's measured in meters, but we call it lambda, which is the sign over here, and is the distance between two crests or troughs. Troughs is the lowest point on the wave, and crest, I think it's the highest point on the wave. Your speed is in meters per second, we call it V, and it is the speed at which a wave is transmitted. Here are a few of your basic equations, and it's 1 divided by period will give you frequency, and similarly 1 divided by frequency will give you period. Then the next equation is your velocity is equal to, well, actually the speed at which a wave is transmitted is equal to the frequency multiplied by the wavelength of that sound. But we can derive a new equation. If we put 1 over t in the place of f in the second equation, we will end up with velocity, or the speed of the sound, the speed at which the wave is being transmitted, equal to the wavelength divided by the period. So please note that the speed of sound in air is 340 meters per second unless otherwise specified. And this is the formula that we will be using in grade 12. It says FL is equal to V plus minus VL over V plus minus VS, all multiplied by Fs. So I've just written a little breakdown of what everything stands for. Please note that your V over here is always the speed of sound in air. It will always be 340 meters per second. In every Doppler effect situation, we are always dealing with a listener or an observer or a detector. It's all the same thing. But basically, we're always dealing with a listener and we're dealing with a sound source. The sound source emits the sound. The listener hears the sound. One of them is always stationary. So for one of them, the velocity will always be equal to 0. Like if I have VL is equal to, let's say, 3, then Vs is going to be 0, because they won't give you a velocity for both of them, at least not at this stage. So just read through the breakdown that I've written here, explaining what everything in the formula means. Okay, so there are 4 different situations that you can have. And in the previous equation, you might have wondered, how do we know when to use plus or minus at the top or plus or minus at the bottom? And here's how we're going to understand when to use what sign. So in the first situation, the listener is going to move and the sound source will be stationary. If the listener moves towards the sound source, I explained earlier, if we move towards the sound source, the observed frequency is going to increase. The sound that we're hearing is going to appear as if it's getting louder and louder. So that means that we want a bigger answer. We want the thing at the top to be big and we want to divide it by something very small. So that means we're going to use a plus at the top because plus is big, and we're going to use a minus at the bottom because a minus is small. You know, the number line goes -2, -1, 0, 1, 2, so it's increasing. So I use that logic to understand that the minus, I see it as something small, and I see the plus as something big. So if I'm moving towards the sound source, the sound is appearing as if it is getting bigger, or it is getting louder. So I want a big answer. It means I'm going to put something big on the top, and I'm going to divide it by something very small. So now, if the listener moves away from the sound source, the observed frequency is going to decrease. The sound that we are hearing is going to appear as if it's getting softer and softer. So we want a small number on the top, and we want to divide it by a big number so that we can get the smallest sound possible. I hope that makes sense. The next situation is where the sound source is moving and the listener is stationary. If the sound source moves towards the listener, the sound is going to appear as if it's getting louder. So we're going to put a big number on the top. That means we're going to use plus on the top, and we want to divide it by a very small number. So that's going to be a minus, so that we can get the loudest sound possible. If the sound source is moving away from the listener, it's going to appear as if the sound is getting softer and softer. So we're going to want to put a small number on the top and divide it by a very big number so we can get the smallest sound possible. Okay, so the uses of the Doppler effect. You can obviously read this in more detail in your textbook. I do remember that in a test I wrote, they asked to explain one use of the Doppler effect and its medical importance for 3 marks. So that means you wouldn't have been able to use the fact that it can detect the speed of a car. You would have been left with these 2 options, and you would have had to explain it for 3 marks. So please do read over that in your textbook. The 3 uses that it has, in really, really brief, is it can monitor blood flow rate, it can monitor the heartbeat of a fetus, and it can detect the speed of a car. So another thing I wanted to write down here, because I did see it in a past paper, if the sound source is stationary, it means that the reflected frequency is going to be equal to or less than the original frequency. So what I'm saying is, when they were explaining how the Doppler effect is used to measure blood flow rate, they said something about how a transmitter emits a sound, and the blood cell reflects that sound back to the sound source. But as it's reflecting the sound back to the sound source, the blood cell is moving further away. So the sound that it's going to reflect back to the sound source is going to be lower than the initial frequency. So I really hope that makes sense, but please try and understand that. Like, if you are emitting a sound of 50 hertz to somebody, and they are moving away from you, and they have to now reflect that sound, the sound they're going to reflect back to you is going to be softer than the one that you had initially emitted. So that's basically what I explained here. Sound source is stationary, reflected frequency is equal to or less than the original. If the sound source moves towards the detector, then the reflected frequency is going to be higher. Okay, now I just want to explain shifts really quickly. So we get a red shift and a blue shift, but basically the light is, or the shift is referring to the frequency or the color of light observed and how that differs from the actual frequency emitted. So with your red light, it has the longest wavelength and the lowest frequency. So that means that the object is moving away. And with your blue light, it means that the wavelength is much shorter. It's got a short wavelength. It's got a high frequency, and it means that the object is approaching. So the thing I wanted to explain about that is the fact that if a light source, for example, a star, and an observer on Earth move away from each other, then the waves will have a longer wavelength and a lower frequency will be observed. So to the observer, it will seem as if the frequency of light decreases, shifting towards the red side of the spectrum. Whereas with blue shift, if the light source, a star, and an observer on Earth move towards each other, it will seem as if the frequency of light increases, shifting towards the blue side of the spectrum. But don't worry too much about that. What you do need to know is how to explain the cosmological redshift. And that means that, so basically astronomers have observed that predominantly redshifts are taking place in the universe. They are observing more redshifts in the universe than blue shifts. And we know with redshifts, objects are moving away. So if an examiner asks you, use the redshift or the cosmological redshift to explain why the universe is expanding, you're going to say it's a phenomenon where predominantly means like more, predominantly the light of a lower frequency, longer wavelength is observed than the real frequency being emitted by stars. Not only because most galaxies in the universe are moving away from Earth, but also because the universe itself is expanding. If we are constantly seeing redshift, and redshift means objects are moving away, then that means that the universe is expanding. So that is all the theory you need to know on Doppler effect. Let us go into a question.